The reason I want to show it to you is because it's a pretty classic example of how they give you a situation with very little information. And just like an exponential growth indicator, you have to draw some conclusions about the equations you're going to have and use those equations to provide whatever information they're asking for. So here you go, look up. There's a spring or some kind of elastic thing. You'll get very sick of this kind of example. You'll think, can't maths teachers think of more examples? And the answer is, yeah, they probably could, but it does just fine and the maths works. So, you might like to draw this. It helps to have a picture. You've got a spring and it's moving up and down. There's like a weight at the bottom. Okay, so like think of like a slinky, I suppose. Okay, now here's all they tell you for the setup. Okay, there's very little information. It takes 4 seconds to go from the bottom of the motion. And they tell you, the closest it gets to the floor is 15 centimeters from the floor. It takes 4 seconds to go from there to the top of the motion, which is 55 centimeters from the floor. I just realized this is a really short room, but anyway, not to scale. Okay, you get the idea. 4 seconds to go from here to here, and I assume, because we're modeling on simple harmonic motion, 4 seconds to come back down again. Okay. Those are the measurements. The last thing they tell you is that it starts, t equals 0, starts at the center of motion moving upward. Okay, full stop. That's it. That's all you need to know to develop all of your equations of motion. Okay, so let's think about this. What's the key data here? It starts at the center of motion. Okay, so that automatically tells you right away which are we likely to choose from our sort of 4 to choose from displacement equations. Which are you likely to choose? Probably sine, right? Because sine starts at the center of motion. Okay, it's moving upward. So are we going to choose positive sine or negative sine? Positive, it goes up. Okay, good. So right away I have this. X is equal to a sine nt. This is what I already know. But I haven't accounted for all of the information in the question yet. Okay. So for instance, you might want to know something like n, which has to do with frequency or period, right? Where do I get that from? I get that from this. 4 seconds to go from the bottom to the top. Okay. Now, just be careful. Just be careful. What would that look like? Just as an example, not thinking about the constant up and down yet. If I'm at the start of here at the origin, right, and I go upwards, and then I come downwards, and then I go up, and so on. Okay. Where is that 4 seconds? 4 seconds to go from the bottom of motion to the top. Well, it happens lots of times, but one example would be in here, right? The bottom of motion to the top of motion. Okay, so that interval on the time axis, that's 4 seconds. Four seconds. So therefore, be careful, what is the period of motion? It's 8 seconds. It's not 4. Classic beginner's error. Okay, you see 4 seconds, and so you jump right in, into 2 pi on n, right? Equals 4. But it's not equal to 4. That's not the full cycle of motion, right? You've actually got to go all the way. Okay, so if I want to work out n, I would say period equals 2 pi on n. Okay, but I know what the period is. It's 8 seconds. Yep. So I can switch these around, can't I? What value do I get for n? 2 pi on 8, which is pi on 4, right? Good. So that's good. I can actually pop that in there. Pi on 4. Okay. Now, I've got my horizontal sort of scale taken care of, right? But I haven't done anything about the vertical. I don't know how far this goes up and down, and I don't know if how far I've been shifted up and down, okay? So you've got this information here, 15, 55, right? 15, 55. What do you think is the easiest piece of information to gain from that with the least calculation? Looking for a couple of different numbers here. What can you see? What am I looking for? What am I looking for? Well, something like, say, the amplitude would be useful, right? The amplitude looks to me like it's from the top to the bottom. It's half of that, isn't it? Right? Because we would say the amplitude of sine is 1. It's not 2, right? So you take this distance, which is 40, and you take half of that, and that would give you your amplitude, wouldn't it? Okay, so my amplitude here, my A, is 20. Okay, that's good, but I still haven't accounted for everything. This equation, as it stands, well, it goes through the floor at the moment, okay? So what can I do to change this so that it accounts for these kinds of numbers? Any suggestions? What did we look at the start of the lesson? What kinds of ways can we modify this equation? I could add a constant, couldn't I? I'd have to move it upwards. How far upwards would I have to move it? It'd be halfway between the bottom and the top. Halfway, right? That reads to me something like 35, right? Because then you go 20 down to 15 and 20 up to 55. So here's one alternative. Okay? So what have I got here? This is my equation of displacement. Okay. Now it bears mentioning at this point, we don't have to write this as our equation of displacement. I've kind of made an assumption here, right? What is x equals 0 in this context? X equals 0. What does x equals 0 represent? It represents a place on this diagram. What place? It represents the ground, the floor, right? So I actually am saying let x equals 0 be the floor. But I don't have to. I can make x equals 0 wherever I like. I could, if I wanted to, I could make x equals 0 be the center of motion, which is 35 centimeters above the ground. Okay? And then I wouldn't have to worry about this constant. I just have to account for it later on if I wanted to work out things like, say, where am I? Okay? All right. So being that you do have that choice, for now, this is what we've gone with. Okay? How am I going to answer part A? It's not that hard. We've done all of the hard work, actually. The hard work was making this guy. Now, if you want to know where you are after 3 seconds, right, because we've formed the right equation, all you have to do is stick t equals 3 and let's do it. When time equals 3, right, I'm going to get x equals 20 sine 3 pi on 4. What's 3 pi on 4? Sine 3 pi on 4? That should be, let's see, from 0 to pi for sine I'm positive, right? And it should be the same as pi on 4 and 3 pi on 4. Should be the same, right? That's 1 on root 2. Plus 35. I can divide through that. That would be 10 root 2. 10 root 2, right? Here I am. Centimeters above the floor. Okay? So if I had, for instance, if I had not chosen this equation, not let x equals 0 be the floor, I could have said this, right? Then when I evaluated t equals 3 down to here, I would get this, right? So then what would you do if that was the if that was your x equals 0 that you chose? You'd have to say this represents a distance not above the floor, but above the center of motion. And you'd say the center of motion's at 35, and you would come up with the same answer, because you'd add that number. Okay? So that's what you'd do if you chose that. How fast is it going? At that center of motion, and because I'm interested only in speed, I don't care which way, right? And it's going to be the same either way, just positive, negative. How do I work out the speed? I need the derivative, don't I? Sorry. By the way, if you do choose to go for x dot and x double dot notation, which is fine, and the questions will as well, can I recommend that you make your dots obscenely large? Because, you know, when you're in a hurry and you write this or you write that, they look really, really similar, particularly when you're in an exam. So if you're going to use dots, then make them huge and unmistakable. Okay? X dot. Here's my equation, right? So when I differentiate, pi and 4 is going to come out the front. So what will be my derivative? 5 pi cos. And of course, our constant 35 just drops off. No problem. So I want to know the center of motion. There's lots of times when I'm at the center of motion, right? What might be a good thing to choose? How about times 0? That's a nice convenient thing to put in, right? So if I put in, when t equals 0, like you pick whatever value is convenient. Obviously, I'm going to be at the center of motion in another 4 seconds. But why would you put in t equals 4 when you can put in t equals 0, right? Especially when you see, you'll just get cos 0, which is 1. So you just get 5 pi, right? So this is a velocity, right? So it should be in meters per second because I've got, centimeters per second. Because I've got centimeters here and I've got seconds here. So far so good? Last part. I want to work out the maximum acceleration. Now, where does the maximum acceleration occur? At the extremities. Good, we're starting to get the rubber band in our head, right? So I can choose 15 or I can choose 55. Either of those would be fine, right? Obviously, it will be going in a different direction, but I'm still going to get the value, right? So you have a couple of choices. What could you do? I want to find an acceleration. What would be the natural thing to do? Differentiate again, right? Because that's how we got velocity, yeah? You'd say x double dot, and then you differentiate this and get something out. Except we're in simple harmonic motion. I already know what the second derivative is. I know what acceleration is because I know what displacement is, right? Right? So this is equal to, now careful, because we changed the center of motion, at least in this equation we did, right? This is not going to be n squared x, minus n squared x. What's it going to be? It'll be x minus 35, right? Now, a couple of things, don't forget, it's actually not n. I know what n is, right? So I'm just going to stick that in. Right, that's n squared, isn't it? And so we said, look, just pick an extremity. Pick 15 or pick 55. I'm going to pick 15 because that negative and that negative will cancel and give me a positive. Is that okay? So, coming over here, when x equals 15, okay, you go x double dot equals, and I've got 15 minus 35 in there. That's negative 20. The negatives cancel, so you're getting 20 pi squared on 16. That's 5 pi squared on 4. Yeah? Now it's acceleration, right? So it should be, that's a terrible 4. Centimeters per second squared, or second to the power of minus 2 if you prefer. Okay. By the way, what would we have done if we didn't do it this way? What would we have done? We would have to differentiate, right? But then, if you differentiate, you're in terms of time. So then you have to work out, now when am I at one of those extremities? You need a t value to put into that because it's a function of time, right? So then you work that out, introducing more places where error comes in, and then you substitute and you should get to the same value, right? But can you see, being that we already know this and we know how simple harmonic motion behaves, take advantage of that. Go straight to the differential equation because you can use it. That's the point.